Hello, everyone. My name is Matthew Kerner. I'm delighted to be speaking with you today at Build. I'd like to ask two favors. Since it's such a large room, it would be great if people sitting closer to the back could move a little bit closer, because I will do a lot less peering that way. And so it would be great if you could move up here. And also, if you have a cell phone that could ring during our talk, it would be great if you could put it into silent mode. I'll be talking about building scalable web apps. And I thought I would start by just reflecting on one of the things that we've seen so far this week. I guess you've all received Windows 8 developer preview devices and builds, and you've gotten to see some of those apps that are on the home screen. And there's been some press and some discussion about how some of those apps were built by interns working in Windows. I happen to be friends with some folks on the team where some of those interns were working. They built the weather app, the stock app, the news app, and the Twitter app. And in all four cases, those apps are backed by Windows Azure services. And the job of the service is to monitor whatever data source that app exposes to the user. And when a user decides to, let's say, add a stock to the ticker, the app notifies the Azure service, and the Azure service records the fact that that user cares about that stock. And then as the stock value changes, the app sends Windows push notifications through the push notification service to the user so that their live tile gets updated. You can imagine that this app needs to scale in proportion to two different things. First of all, the set of stocks that users add, and second of all, the set of users that are out there. Until Tuesday, things were pretty simple. There were a couple thousand engineers working on Windows who had access to these applications, and so those Azure hosted services just ran along. And then Steve Ballmer told us on Wednesday that there were 500,000 downloads of the developer preview build on Tuesday night. So you can imagine that overnight, adding 500,000 new users was quite a surprise. And so I would just like to poll those people in the audience. Who here has built a service that's out there running on the web today? Okay, lots of hands. That's great. Of those folks who've built a service, how many of you would feel comfortable if tonight you had 500,000 new users? I don't see a single hand. So fortunately, these interns who built these services that back the demo apps that we put into the preview build, built them on top of Windows Azure, and they built them in such a way that they could be scaled up to handle the load. And at least as of yesterday, when I spoke with one of my friends on that team, he gave me the thumbs up. Everything is still running fine. So what I would like to do today is speak with you about how you might go about building scalable web apps on top of Windows Azure. I will assume that you already know something about Windows Azure. And if you don't, what I would recommend is actually take this time and go watch one of the previous talks that's an overview of Windows Azure, get up to speed on it, and then you can come back and watch this, and it will make a little bit more sense at that point. And what I'll be doing is talking about three specific areas. The first is how to design synchronous and asynchronous applications. Async apps will scale much better, so we'll talk about that. We'll talk about managing data access between your customers and your service, and also between the different tiers of your service. And finally, we'll talk about application tuning, specifically with respect to Windows Azure and how that applies. And at the end of this talk, what I'm hoping is that you will all feel comfortable raising your hand and signing up for 500,000 additional users and all of the excitement and revenue that that can bring along with it. The first topic is talking about design patterns. Would anyone in the audience like to volunteer a working definition for a synchronous design? Yes? The caller waits for work to be done. It's synchronous. I like that. And I'd add one further point, which is that while the work is being done and the caller is waiting, the caller is not available to do anything else. And that's the main issue with a synchronous application. Let me give you an example of how that might look. Let's suppose we've got a Windows Azure service, and it's got a single web role instance, and that single web role instance has a single thread. When a client request is delivered to the thread might go dispatch that request to the middle tier or data tier. And then because it's a synchronous app, the caller will block, waiting for the work to be done. And that might take a long time. In fact, during the period of time that the caller's blocked, another client might make a request. And although that thread is not doing anything meaningful, it won't service that new request until lots of time passes, and the first response returns from the middle tier or data tier. At that point, it'll dispatch that response to the first caller, and it will only then be able to service the second client request. The key point is, each thread in this design will be able to handle one request at a time, whether it's busy or not. And it scales poorly because as you add a new thread and you take all of the overhead of allocating a new thread stack, you only get the ability to handle one additional request at a time. And ultimately, if you want to scale this app up to handle hundreds of thousands of users, you're going to be in a situation where you need a tremendous number of role instances, which will ultimately become expensive. So it can be very nice if instead you can adopt an asynchronous design approach. Let's take a look at how that would work. Suppose that the same thread receives the client request, and it goes ahead and it dispatches it to the middle tier. Up until now, everything's been the same. Now, instead of blocking, this thread will somehow record the fact that it dispatched that request to the middle tier, and then it will wait for the next useful piece of work that comes along, which could be the response from the middle tier, or, as in the previous example, it could be the next request from a client. At that point, this thread can dispatch that request to the middle tier, and now we've got both requests in flight with the middle tier at once. And again, the thread is waiting for the next piece of useful work. At this point, when, let's say, the second response comes back from the middle tier, the thread can go ahead and dispatch it to the first client. And again, once the first response goes, it can do the same. This is a much better design because this single thread can handle multiple requests interleaved with each other, and it's never spending time blocking while there's useful work to be done. There are some downsides to this approach. One of those downsides is the overhead associated with the bookkeeping that you need to do in that data structure. And that overhead might not just be, let's say, CPU cycles. You could have contention on some shared data structures, so you need to be thoughtful about how you structure that. The other downside of this approach is that the code that you need to write in order to track this outstanding context can often make it difficult to understand or maintain your application. And so one of the things that's available to you that can simplify this is the async programming model. There have been a few talks on async already. I'm not going to go into it in great depth, but I do want to show you an example of that because it's a really useful approach for building these asynchronous apps while still keeping them maintainable. Let's suppose that we had a method that was responsible for processing the upload of an image, and it needs to do two things. The first thing it will do is it will record the fact that that image has been uploaded in a SQL Azure database, and then it will actually push the image into a blob in blob storage. There are lots of things that might be wrong with that design, but for purposes of this example, let's suppose that that's how we do it. And I'll talk more about some ways to mitigate that going forward. And we're going to do that synchronously. We'll go ahead and we'll call some helper function that adds the URI of the image to SQL Azure, and then we'll actually upload the image to the blob. And we're passing in a cloud blob here. A cloud blob is one of the types exposed in the Windows Azure Storage Client library. It's got a method that allows you to do the upload. So this is the synchronous version of the method. Very easy to understand, but we're going to block while we're updating SQL, and then we're going to block again while we're updating Windows Azure Storage. Here's an async version of that same method. You'll note, first of all, that I'm using the async keyword. And I've changed the type of the return value from void to task. The task is the unit of bookkeeping that this async model uses. I've also added async as a suffix at the end of the method name. That's something that we do by convention just to indicate that we're adopting the async model here. And it takes the same parameters that I previously accepted. Now, instead of just calling add image to SQL, I'm going to create a task that represents an async method invocation to the async version of that method. And I'm going to do the same thing with the method to upload to a blob. And then finally, what I will do is I will await the results of those tasks. And you can see that I'm using a task combinator to say that I don't want to return from this method invocation until both of those subtasks have completed. And there are a variety of combinators available in the CTP that you can try. Now you might say, okay, this code's very clean, it's easy to understand, it's now async, which is great, but I seem to have done something magical. I've taken some code and just sort of put in some keywords. How does this actually work? Well, really the question is, how do we make one of these async helper functions? So let's drill down one more time and see how we create one of those. Sorry, this clicker works only when I'm close to the machine. You may have noticed, if you've spent time looking at the Windows Azure APIs, that in many cases, the API, the helper functions, provide both a synchronous method and begin-end method pairs that use the iasync result pattern to allow you to do your own bookkeeping, to build your own async application. Well, the async CTP provides an easy way for you to create an async method out of these begin-end pairs that works in this model. Let's suppose that this is the helper function to upload the image to the blob. I'm just using the synchronous function that adds a stream to the contents of a blob. Very straightforward. Now what I'm going to do is create the async version of that. I use the same keyword. I've added the same async suffix by convention, and I'm accepting the same arguments. And now what I'm going to do is I'm going to use the task factory static class in order to go ahead and create my task that I need. And so what I've done is I've said task.factory.fromAsync, ignore the generic for 1 second, and you can see that I've passed in the method that's the begin method of the begin-end pair as the first argument. Then I've passed in the end method from the begin-end pair as the second parameter. And the third parameter is the image that I'm passing. Now that image is actually an argument to begin upload from stream. And since it's of type stream, I've populated the generic with type stream. And finally, I'm going to pass a context parameter. The context parameter is actually very useful when you use the begin-end pairs and you use your own iasync result plumbing, because you sometimes want to pass some context through so that when the end method is called, your delegate will be able to access that and use it. In this scenario, it's not really meaningful because the task structure is taking care of all of this for me. So I'm just passing null in that case. And I'm awaiting that task that I created. And that's it. I've now created an async method out of a begin-end pair. And this is how you sort of ultimately get down to something that's async at the bottom. Now, if you like this and you want to use it in Windows Azure, you can do so. This is in CTP now, based on .NET 4.0. It will be available fully in .NET 4.5. But since it's a CTP, it's not present by default in Windows Azure. So all you need to do is to make sure to carry async CTP library.dll as a copy local DLL in your project, so it'll be present in the cloud. And at that point, everything will work. Unless you have a project that relies on dynamic compilation of code at the server side. And if you rely upon that, it's a little bit more complicated. Come see me afterwards and we can talk about how to make that work. The async programming methodology is great for achieving fine-grained parallelism in your code. But there are other sort of scopes of parallelism that you might want to exploit in your application to make, say, the communication between different parts of your application async and scale those different parts out independently. So one useful component that the Windows Azure storage library exposes to you are Windows Azure storage queues. You could imagine that you might have a front end. It receives requests from users. And each time it receives a request, it first authenticates the user and then authorizes them and then perhaps passes that request to a middle tier. One way of doing that is to queue that request on a Windows Azure storage queue. The operation of enqueuing a message is very quick, and then your front end can go on and process the additional requests that it receives. Meanwhile, that item can sit in the queue, eventually be dequeued by a middle tier and processed there. And so this provides a nice asynchronous communication mechanism between your front tier and your middle tier. Another nice property of queues is that they effectively act as load balancers. Let's suppose that you have one middle tier role instance that's very busy. It's processing many requests and there's no thread available to process the next request. Instead of having your front end synchronously call that over the network and wait for a long time until that role instance is prepared to process the request, request can go on the queue, and whichever role instance in the middle tier is available will go ahead and dequeue that message and process it. So you'll get the load balancing across your middle tier. The other nice thing about queues is that they're inherently redundant to failure of individual role instances. Let's suppose that you enqueue a message. Your worker role dequeues the message and starts to process that message, and then it crashes while processing the message. Of course, all of the, even if you write perfect code and you never experience a crash, all of the things that run in Windows Azure run on commodity hardware, and it's conceivable that we could lose a physical node while that request is in flight. One of the things about Windows Azure Storage queues is that when you dequeue a message, it doesn't actually cause the message to be deleted. It just causes the message to turn invisible for a period of time that you control with the invisibility timeout. And so if by the end of that time window, the message hasn't been explicitly deleted by the guy who dequeued it, it will become visible again and reappear in the queue so that another worker role instance can dequeue it and complete the work. So that's one of the nice properties of queues, is that they provide resilience to failures. Now you might think to yourself, there's all this async stuff going on, and messages can be processed twice. What if a role instance processes a message, and it's about to delete the message, and then it crashes before it deletes the message? And now the message will get processed again. What do? We could end up with inconsistent data. Somebody could order something twice. They could be charged twice. All of those unpleasant things. You have to handle this in your application, and this is one of the very difficult things about building apps that are resilient to failure. And so we encourage people to adopt designs that utilize eventual consistency and item potency to make sure that these kinds of things can be processed twice without compromising the consistency of the data. You can also use transactional semantics, for example, with SQL Azure if you prefer. But this is one particular kind of problem that always exists in any kind of system, but it becomes further exposed when you adopt an async design pattern, because there are more windows of time when you have work in flight and it may not be completed and you could experience a failure. So this is just something to be aware of. That takes us to the end of our discussion of design patterns of applications, and now we'll be talking about managing data access. And the trick here is that there are different approaches to managing data access depending on the location and the nature of the data that we're talking about, and I'll walk you through a number of different ones. And the bulk of the time that we spend for the rest of the hour will be spent on this topic. Let's suppose that we have some public content that's available in blob storage, and we have a hosted service that makes that content available to users. So they might request a web page, and then the web page goes and returns them some HTML with a link to an image. They go back to that hosted service to retrieve the image. The image turns around and gets it from blob storage and then returns it to the caller. Well, the first trick is rather simple. You should just get out of the way. It's much more efficient if your customers go directly to blob storage, because blob storage scales out very elegantly. And your hosted compute can remain rather small and be responsible just for generating HTML. This is useful for all kinds of public content scenarios, whether it's images or videos or audio. So this is sort of a straightforward one. Now, what about scenarios when you have content that you'd like to serve directly from blob storage, but that content is not publicly available? Perhaps it's paid content, or perhaps it's content that is preceded by the presentation of an advertisement, and you'd like to make sure that your customer sees the ad before they see the content, that the ad is responsible for funding. In that scenario, you can still direct your users to blob storage, but you can't do it the same way as before. Instead, you can use something called a shared access signature. So let me describe how that works. A shared access signature is a URL that provides a certain set of rights to a certain set of content for a time window. If your customer, first of all, contacts your hosted compute service and wants to access that private data, your hosted compute service can return this URL to the customer that they can then use directly to talk to blob storage. And the way that you do that is that your hosted compute app has the key for accessing your storage account. And that key need not be exposed directly to customers, because that key essentially gives them ownership of the storage account for all intents and purposes. So, Bob says, hey, I'm a paid user, I'd like to see X. And you make a decision about whether Bob is in fact Bob, and if he is Bob, whether Bob is permitted to see X. And then if you decide that that should be granted, you construct a URL, and it says, the holder of this URL ought to be able to read X for the next 10 minutes. And then you sign that URL using the shared account key, and you return it to Bob. Now, anyone who possesses that URL will be able to access that content. So if Bob passes it on to Eve, Eve will also be able to access the content. And for that reason, we recommend that you use HTTPS to return that URL to Bob so that anybody who's sniffing on the network is not going to be able to see that. And then Bob goes ahead and simply issues the request using that URL. Windows Azure Storage inspects the URL, confirms that the signature is valid, looks at the specific piece of content you're trying to access, and compares it to the access that's been granted in the URL, and also checks the time. And then if it likes it, it'll go ahead and return the content directly to Bob. And so that's how you can get out of the way for private content. Now, imagine that you had a system that was a backup service where you pushed online backup content to Windows Azure from your customers' machines. You can use this to get out of the way for content that you write as well as content that you'd read. It's just a different privilege that you're going to put in the shared access signature. So you can issue shared access signatures to say, push data up to this particular place. This is an example of one of the things that you can do to improve that helper function that I showed you previously. It really doesn't make sense for your hosted service to write the contents of an image to a blob unless it itself is generating the image. If a customer is generating the image or providing it to you, you can have them push it directly to blob storage. And by the way, since it's just an HTTP post, they can do that from any kind of device that supports HTTP. It doesn't have to really be a rich client that has the full storage client library, for example. There's a blog post that talks about how to do this that Steve Marks wrote that's really great, so I'll just point you there if you're curious about getting this going. By the way, there's a more complicated version of this where you can express the container access policies on the container itself in blob storage and then just reference those in the URL, and that enables you to do fancy things like, say, revoking the access earlier than the time of expiry. And so all of that is also detailed in the SDK. It describes how to set those up. The next thing I'll talk about is what happens when you've got users located around the world. We've got 6 Windows Azure data centers, and you could conceivably put your content in all 6 of those data centers. But even if you do that, there are still plenty of users who are not located right next to one of those, and they may have a difficult time getting to that content. You may also find that all of the demand from all of those users around the world is concentrated on these individual pieces of content, and you can actually hit some of the scaling targets of Windows Azure Storage. So how do we get around that? I'm imagining sort of like a Patch Tuesday type scenario where everybody in the world is going to download the same piece of content at exactly the same time. There's a CDN built into Windows Azure, and I'll show you how that works. What we do is we locate the CDN at a number of different peering locations around the world so that it's located just a few hops away from customers, even if it's many hops away from the origin of the content, in this case, blob storage. When a customer wants to access something through the CDN, they issue a DNS resolution request using a special DNS name that we give you when you turn the CDN on. And we have some logic to automatically resolve that DNS name to the closest IP address for the point of presence around the world that best matches that user. When the request arrives at the CDN decides whether the content that's being requested is locally cached. And if it isn't cached, it in turn goes and retrieves that content from the point of origin. Again, in this case, it's blob storage. And then once that content is stored in the CDN, there is a time to live header in that content that determines how long it's kept there before it's purged from the cache. And any user who requests that content will receive it from the CDN point of presence rather than the point of origin. You can imagine that the first user who's unlucky enough to try to get this content from that CDN location will actually have a worse experience than they would have gotten if they went directly to blob storage, because there's an extra hop in between. However, every subsequent user will be served directly from there. And so if you have content that you think is going to be accessed more than once within a particular geography, it probably makes sense to use this because the vast majority of your users will get a better experience. And the load on your central storage account will go way down in addition to the latency that's experienced by your users, so you'll scale better. And indeed, when Microsoft releases patches on Patch Tuesday, we do use this technique in order to distribute those patches from a point of or from a point of presence that's close to the users who are downloading it. The way that you turn this on, it's pretty simple. You go into the developer portal, you click a button, the CDN is enabled, and you are given a URL. For example, the URL might look something like this. And so if you access the content through this URL, you'll go to the closest point of presence. And if for some reason you want to access the content from the point of origin, you can always use the standard Windows Azure storage URL and get it from there. If you don't like the look of the URL that we give you, and many people don't, you can use a CNAME and just set up whatever you like. And again, Steve has a great blog entry on that. We collaborate on these things, so there's always a blog entry for anything that I want to talk about. And people have said to themselves, well, I'd really love to use this for video, but it only makes sense if I have smooth streaming, because otherwise my customers get a poor experience. It's not generally available yet, but there is a CTP. If you're interested in participating in that, come chat with me afterwards, and we can get you in touch with the right people. And so that will be coming. The obvious question that you might be asking yourself next is, there's this content in the CDN. How long is it cached for? How do I make sure that it's cached for just the right amount of time without it getting stale? So that's the next thing we'll talk about. By default, when you use the CDN, we cache that content for 72 hours. And you can control how long we cache it by setting a time to live value in the content header. And there's a way to do this as a property of the blob in Windows Azure Storage. That's in seconds. Although it's expressed in seconds, I encourage you to think big here. Weeks is a great amount of time. Longer than that is a great amount of time. And the reason that that's really valuable is because you'll be giving more of your users a much better experience. And you won't only be leveraging the Windows Azure CDN, you'll also be leveraging all of the downstream caches on the internet, whether it's proxy caches or browser caches. And so you may, in fact, be serving requests from these other caches that you don't even know anything about and that you don't pay for. So it can significantly reduce your cost as well, because you won't be paying for storage transactions or bandwidth at that point. The trick to avoid getting stale content served when you have very long time to live is to use versioned URLs. Let me give you an example of that. Let's suppose that I came up with a logo on August 1st for my company. I'm happy with it. I think it's going to be in use for a long time. So I set my time to live to a very large value. And then in my HTML, I referenced that logo. And you can see that in the name of the logo, I've embedded the date on which I published that content. Now, if I decide, as of today, that the logo's no good, I can put a new piece of content side by side in the point of origin, and I can just version the URL with the next version. I change my HTML, the new content gets pulled into the cache, the stuff lives in the cache for a very long time, and no user ever receives a stale piece of content. Conveniently, if I decide that I like the old logo better, it'll still be present in blob storage, so I can roll back to it. And if I decide I want to test it out and give, say, a small fraction of my users the new logo while I keep the old logo for everybody else, I can do that side by side as well. So I can do some A/B testing. So this ends up being a convenient technique to take full advantage of the CDN without ever serving stale content to users. Now, I've shown you how to use the CDN for static content and how to control the time to live. But sometimes it's convenient to use the CDN for dynamically generated content, even if that dynamically generated, only if that dynamically generated content is relatively stable, in the sense that I might visit your web app, I get a page, I go back and visit it again, I get the same page, but it's generated dynamically. In that case, you can actually use the CDN and set your point of origin to your web app. And it works the exact same way that it did before. The CDN point of presence will go access the content from your web app and cache it locally according to the time to live. You can use the original URL if you want to get it from the web. You can use the CDN URL if you want to get it from the CDN. But one little gotcha here is that the CDN doesn't retrieve it from the original URL. It inserts this little CDN prefix at the beginning of the path. So you have to make sure that your app is designed to return the content from that path. If you want to use HTTPS or your own URL, you're welcome to do so. All of that works. And again, there's conveniently a blog posting that talks about how to do this. One issue that people can run into when they do this is that they forget to set the content control header correctly, but they never notice that the request is not being served directly by the CDN because IIS's output cache kicks in and your code never gets invoked. And so you think it's being served by the cache at the CDN when in fact it's being served by the cache that's closer to your web role. And so Sean has written a blog post talking about that, both indicating what you can do in code to set the time to live correctly, as well as suggesting some approaches for diagnosing this kind of problem by inserting some logging at the right point in the request pipeline. So I've shown you how to use the CDN for static content, and now I've shown you how to use the CDN for stable dynamic content. What about truly dynamic content, something that changes every time that you want to serve to your users from the best possible location? Well, what we've done is we've taken parts of the CDN that are applicable in that scenario and separated them out into this Windows Azure Traffic Manager. And the idea here is that you might have a user who can access any one of possibly many hosted service deployments at different places around the world. And when they issue a DNS request to access that hosted service, we can return them an IP address that's the best match based on a combination of policy that you set as well as monitoring that determines which of your hosted services is available. And then that response is returned and the customer will access the hosted service that's the best match. You can use CNAMEs again. You can use this for a variety of different scenarios. Perhaps, for example, you just want to offer the best performance, or maybe not. Maybe you just care about disaster recovery. So you want to be able to redirect your users to a site that's available if the primary site is down. Or perhaps you have business reasons why you'd like to direct users to a particular site in a particular locale because of data sovereignty concerns or perhaps tax concerns. So it can be useful for all of that. And this approach is not exactly the same as the CDN because we're not actually caching the data. The only thing that gets cached is the DNS response at the client side. So we've taken the part of the CDN that's applicable for dynamic content and made it available to you. Now, when you do this, we provide some ingredients and you provide some ingredients. The ingredients that we provide are a database of geography IP mapping, so we can figure out the best location to send users to, as well as the results of some measurements that we take periodically to determine connectivity between different places in the internet and also the performance of those links. And you provide policies as well as monitoring related data. Specifically, when it comes to monitoring, you give us a URL that you'd like us to monitor. We periodically poll that URL to make sure that it's available. If one of your services goes down, or my remote goes down, we will ultimately notice that and take it out of rotation. And so you can set up this monitoring however you like, and then we'll just make sure that your users get directed to the instance of the service that's available. This is available in CTP. It's not set up for production use, so there's some caveats as I've noted here. But other than that, you can try it out and see if this works for you. So now, whether you have static content, stable dynamic content, or truly dynamic content, you can direct your users to the best location to retrieve that, which gives them lower latency and also scales out across effectively many different sets of resources that can service your users' requests, so you can handle many more users at a time. That takes us to the end of our geo-distributed section of this conversation. And instead, we'll be talking about managing data access between tiers of your application. In-memory caching can be a really useful technique for managing hot data when you have a large number of simultaneous requests. It doesn't work for every class of data because it doesn't provide the same durability and serializability guarantees that you might get from a database or from Windows Azure Storage. But what it does do is it allows you to very efficiently store and retrieve hot data that might be immutable, so everybody can read it and it's always the same, or that varies on a per session basis, so that, let's say, only one front-end role instance would ever be updating that data at a given time. So you don't have to worry about the same consistency concerns that you might have with data that could be updated simultaneously from different places. And this data can just be put into a distributed in-memory cache so that the load on your data tier goes way down. And that means that the requests for data that is actually present in the cache will be satisfied with much lower latency. And since your data tier is not under as much load, it will be better equipped to handle whatever the load is that does get through. And not only does it improve latency, it actually reduces costs because, at least, for example, in the case of Windows Azure Storage, you pay for storage transactions. So the more you can serve out of the cache, the fewer transactions you'll have to pay for. Windows Azure App Fabric caching is our hosted in-memory cache that we provide as part of the service. It's in production, it's got SLAs, and it's located at each of the data centers around the world. So if you are building an app and you'd like a cache to be present close by, it is. The access control service controls the visibility of the cache to callers, so it can be set up in a relatively flexible way. And there are some advantages of this over other in-memory cache options that you might be aware of. For example, if you were to use memcached, you would be responsible for setting up the cache yourself and administering it. All of that is taken care of for you when you sign up for this caching as a service. Also, ASP.NET provides these you can just set up your IIS configuration to use an output cache or a session state cache and point it at this. And so just with some config settings, you can have this light up in your application. You don't have to write any code, although you're certainly welcome to write code if you'd like to. And there are APIs that exist for doing that. Those APIs are symmetrical with the Windows Server App Fabric version of this product. So if you want to write code that's portable between the cloud and an on-premises scenario, you can do so. It simply requires a recompile, and that same code will work. Finally, if you're comparing, for example, against memcached, Windows Azure App Fabric has what we call a near cache. Let's suppose you have a role instance, and it's caching it's using the cache to retain really hot data. The hottest of the data will be stored locally on that node. It won't even be transferred over the network, and it won't even be serialized. So the performance of that near cache is really great, and without having to implement your own cache in your own code, you kind of get this for free, and so that performance is excellent. I believe there also might be a maximum object size limitation with memcached that does not exist with Windows Azure App Fabric caching. I mean, I guess there is a maximum size, but it's significantly larger. The last topic that I'll talk about with respect to managing data tier access is the topic of sharding. And sharding is essentially an approach where you can scale out your data tier. Let's suppose that you have a multi-tenant service deployed on Windows Azure, and you have a number of different tenants all hosted within the same SQL Azure database. And then for whatever reason, whether it's the size of the data that you're storing within that single database, or the number of different queries that you're issuing at the same time against that database across all of these different tenants, you exceed the maximum set of resources available on a single physical node. Well, at that point, SQL Azure will begin to throttle you, and you'll get much worse performance. And in the case where you exceed the maximum size of the database, you won't be able to make any forward progress until you delete some existing data, which may not be an option at all. What we recommend in that scenario is to create multiple databases and to partition your data across those databases in such a way that your application is aware of the partitioning scheme so that it can issue the queries to the correct database, it can distribute the data to the right place, and so on. And this can be useful for a variety of different scenarios. Any limit on a single physical machine is one that you might consider, and if you care to see the full list of them, they're in this document here. The same thing holds true to some extent with Windows Azure Storage as well. Tables are partitioned in Windows Azure Storage to begin with. You define a partition key when you create a table. However, there are some limits that apply to a Windows Azure Storage account. And so it can be useful to use multiple accounts if you expect that your application is going to hit those limits. And there are a variety of such limits. They're visible also on the net. I've got a couple of them here. And so just as you might partition your databases, you may want to do the same with your accounts. And of course, it makes sense to be thoughtful about what partition key you use with your Windows Azure tables, as well as the content that you put together in single blobs, because there are limits that apply to both table partitions and blobs. It's relatively easy for me to draw this picture and say that you ought to put this data in different places. But when it comes to actually implementing this, it isn't so easy. You've got to do a lot of work. And so SQL Azure, that team, has been working on something called SQL Azure Federations, which is a native implementation of the sharding pattern within SQL Azure. When we talk about sharding, it's a pattern, and it's a pattern that distributes data across multiple partitions so that they can each execute independently in parallel without sharing resources. It's also a choice that impacts a number of different things in your application. It impacts your schema, it impacts what your DBA does in their job, and it impacts your code. For example, you have to know to do these app-level joins if you want to look at data across multiple shards. SQL Azure Federations simplifies sharding by taking on some of the complexity associated with these design trade-offs when you need the scalability that sharding provides. One thing that it does is that it automatically distributes data across multiple databases. And so you don't have to worry about putting that data in the right place to begin with. All you need to do is specify which columns in your tables act as the partition key. The next thing that it does is it automatically handles routing of your queries. You use a single database connection string. Your SQL code, much in the way that it would say use database foo, now says use federation foo. And then it automatically points at the right replica of the database across this set of shards for the query that you issue. And the last thing that it does, which is really cool actually, is it enables you to repartition your data without any downtime. So let's suppose that you had, 2 customers in one database and 2 customers in another database, and one of those 2 customers all of a sudden acquired another company and became really busy. Well, you could go ahead and you could just say, look, I need to split that database that has those 2 customers into 2 separate databases, one dedicated per customer. You can do that without any downtime, and SQL Azure will automatically handle that for you. This is available in CTP form now. I believe the CTP is full, but again, if you're interested, you can come speak with me and we can put you in touch with the right folks. And there's a lot of documentation available. We actually happen to have an expert in the audience today, so if you have questions about this, please come up afterwards and we will answer all of those questions. And I think this is really an example of a place where the platform can do a ton of work to make it easier for you to build scalable applications by handling some of these low-level operations as just a facility that we make available. That takes us to the end of our discussion on managing access, data access, either from your customers to your service or between the tiers of your service. And now we'll move on to talk about application tuning. This part of the discussion is really the same discussion that we would have if we were talking about building apps on Windows Server. But there are a couple of Windows Azure specific techniques that might be valuable. The first thing that I'd say is people often go and try to optimize the wrong thing. So you ought to measure what your bottlenecks are and optimize the things that are the bottlenecks so you don't waste your time. And then there are some simple techniques that people are aware of for optimizing IIS-based applications. All of those apply in Windows Azure because Windows Azure uses full IIS. One common element or ingredient of those techniques is to change IIS settings. And a simple way to do that is that you can create a startup task in your Windows Azure project, and that startup task can reference app command, which will modify your IIS settings. That way those settings will be modified every single time a role instance initializes. You'll never miss it. And it can just be taken care of sort of in the standard flow of your app. There are some things that people forget. Don't forget these. You should build in release mode, not debug. It'll be much better. Although Dev 11 supports IntelliTrace in production, we do not recommend it on Windows Azure. First of all, because the Dev 11 tools are not yet compatible with Windows Azure. Second of all, because there's some wiring that we do in Windows Azure to sort of start this up, and that hasn't yet been set up in such a way that it's ready for production usage. And so that's both a performance and a reliability concern if you are using this in production. Also, there's failed request tracing, which is a very useful facility in IIS and ASP.NET, but don't use it unless you need it, because every single request is in fact traced under the hood, and so there's overhead associated with that. It's just that the traces of failed requests are the only ones that are retained. And that's a setting that can significantly impact your performance and your path length on handling web requests. Finally, Windows Azure has this really nice facility that it provides elastic scalability for your different roles. And so if you've got a web tier and you think you're going to have a lot of traffic, you can create many role instances to handle that traffic, or scale it down if you don't need them. One convenient approach that people like to take is that they like to call the Service Management API from their application, so that their application can essentially manage its own scaling based on whatever the signal is that's most appropriate for your workload, whether it's a queue length, or the latency of requests, or the number of requests per second that you're handling. So you can, in a sense, do some auto-scaling. In addition to the things I've talked about already, I would encourage you to confirm that all of the content types that you're using in your application have dynamic compression enabled. That can really be a bandwidth saver. And these, for example, are not enabled by default. And so these are ones that you might want to enable in your IIS configuration. Application pool recycling is great for masking the effects of things like memory leaks. You should tune it in such a way that it doesn't occur at your peak workload times, and you can use that app command trick to do so. There's a blog entry that goes into more detail on that particular example. This is not an excuse for not fixing memory leaks. I recommend you do so. That will impact performance of your app all the time, even if it continues to run even in the face of these leaks because of the recycling. The output cache and the session state cache by default use local disk space, and that disk space will be allocated on the disk where your web app is running. In Windows Azure, that disk is not particularly large, and that can limit the effective size of your cache. So something that people like to do is to create a resource volume in the definition of their role, and then use app command to relocate the cache to that volume, which can be much larger than the default volume that you're allocated. So that's a way to make maximum use of those caches. Finally, Windows Azure Diagnostics is commonly used by people to look at instrumentation data from their applications to make sure that those applications are running the way that they expect. One of the features of Windows Azure Diagnostics is that it can be reconfigured dynamically at runtime to either increase the verbosity of information that's being collected, decrease it, turn on or off different types of data that's being collected. Perhaps you don't need traces all the time, but you want counters all the time. And you can also configure Windows Azure Diagnostics either to upload that data to Windows Azure Storage automatically or on demand. And it doesn't require redeploying anything in order to do this. There's a runtime way of controlling it. So I would encourage you to check out the session that's actually running at the same time as this session and that's being recorded. And you'll hear more in that session about how to dynamically control Windows Azure Diagnostics so you can tone it down so that it's not running with the most verbose settings all the time and costing that overhead. Excuse me. That takes us to the end. We started off with a synchronous application. We made it asynchronous, and we used the new async language features to do that in a way that preserves the readability and maintainability of our code. We took our public content, put it into blob storage, and got out of the way so that our customers can access it directly. We did the same thing with private content and shared access signatures. And then we used the CDN to serve that content from the edge so that it's the closest to the user that it can be. We used versioned URLs and time to live headers to control how long that content would live in the cache without ever serving stale content. And we also pointed the CDN at our web apps so that it's not just useful for static content, but also for stable dynamic content. Then we used the traffic manager and created multiple geo-distributed service instances that are all fronted by a common DNS name that's automatically load balanced based on policy and monitoring to point our customers at the right location. At the back end, we inserted an in-memory distributed cache between our compute and our data tier, and then we sharded our data at the back end. Finally, we tuned our application, and now I think we're in a position where we can all bravely raise our hands the next time someone volunteers to give us 500,000 users overnight. And what we've done is really taken advantage of a whole bunch of features in the Windows Azure platform to make it easy for developers to do these things without having to invent everything from scratch. If you're curious about any of this information, there are a number of sessions that touch on aspects of the talk that I gave and that focus on those particular topics. Async is one that really warrants some investigation because it's so easy to add that support to your application that it's possible to do it too much, and there's actually some overhead associated with the various operations that are inserted by the compiler in the runtime when you use async. There are some great tips in the IIS optimization talk that I'd point you to. And of course, there are some tricks for building global and highly available apps on Windows Azure. Some of them are the same as the tricks that you use for scalability. Others are different. So check all of these things out. And I would now implore you to give me feedback. You can open up your browser right now and enter it. We haven't been getting a lot of feedback at the conference, and we really do appreciate hearing what we could do better and what worked out well. So please do give that feedback. And I'm happy to take questions, which I'd encourage you to give at the microphones. All right, I've answered everyone's questions during the talk. Yes? How fast is the SQL? How fast is the replication between SQL replicas, especially for data that's real-time data? So let me just make sure I understand the question. There are two kinds of replication that you could be referring to. One is every single time you write to SQL Azure, that write is replicated to multiple SQL machines with a high availability configuration that's very similar to the high availability configuration that you would set up if you set up your own clustered database. We make sure that we commit, I believe, on at least 2 of the 3 machines before we return to the caller. All of those machines are located in the same data center on the same network. It's very fast. The machines are optimized in such a way that a SQL workload will run. I don't know the numbers myself. I would point you to the SQL team for the specifics there. There's a different kind of replication that you might be talking about, which is replication between geographies. SQL, by default, does not replicate its data between multiple data centers. Windows Azure Storage does. We announced that at this conference. We don't, at this time, provide an SLA around that, but we do attempt to really keep that reasonably up to date. All of that happens asynchronously for Windows Azure Storage. So there's no performance penalty or latency penalty in return for having that geo-replication. The same can be set up by you for SQL Azure by using SQL Azure Data Sync. And in that case, I'm not particularly familiar with Data Sync, but I believe that there are some settings that control how frequently that kicks in, and that will be governed by the network latency between the different sites. Of course, that's also not something that affects the latency of the queries that you issue because it also happens asynchronously as sort of a background process. I don't know if I answered your question. I hope I did. Yes?
Say you have a hybrid model where you have an on-premise instance and several geographies with your instance running. Can Traffic Manager intelligently route to your on-premise instance as well?
That's a very interesting question. Can Traffic Manager route to your on-premises instances as well? routing, can you give me an example of what you might have on-premise that would play in this hybrid scenario?
This exact same copy on Azure.
Ah, I see. So let's say you have a hosted service. It's deployed on Windows Azure in perhaps a couple of data centers, and you have that same service deployed on Windows Server in your data centers. Is there a way for Traffic Manager to include those data centers? No, there isn't. However, there are plenty of traffic managers out there in the world. Some of them can be controlled in a very flexible way. Ours is kind of integrated into Windows Azure and optimized for Windows Azure, so ours doesn't point at external things. But if you wanted traffic management for sites in general, you could set up your own and you could achieve effectively the same result. It might just take more effort to configure everything. There is another scenario that often comes up when people talk about hybrid applications, which is that they might, for, say, compliance reasons, choose to put their data tier in an on-premises environment. And perhaps they want to restrict access to that on-premises environment so that only certain apps running in the cloud can access them. They're not, in other words, visible on the internet. There's a mechanism called Windows Azure Connect that allows you to install an agent both in the cloud and on-premises, and it creates a secure VPN connection between the cloud and the on-premises assets. And so some of our customers like to do that. You can use this, for example, to join VMs that are in the cloud to your domain on-premises. Yeah?
Thank you for your time today.
Sure.
Question about the starting of federation.
Yeah.
Nice choice to drive it down to the connection string level.
Mm-hmm.
Getting used to hear my feedback. Excuse me. Can you leverage the federation libraries in a data ingest subsystem that's like SSIS, either on-premise or if that data ingest subsystem is up in the cloud? Is there any limitations on the use of that library?
If you set up a SQL Azure Federation, it will be in effect for the database in SQL Azure that you have applied it to. And so when you create the schema for that database, you'll indicate the partition key that you want, and you'll indicate the split points that you want for that data, and then that will just apply. So any process, ETL process or ingestion process that you point at that database will be feeding data to a database that's federated. There is a portion of the T-SQL syntax that's been augmented to support this.
Okay.
In the same way that, as I said before, you'd say use database, you now have to say use federation. I don't know myself whether that's required at the time that you're inserting data into the database. I believe it is, and so you have to make sure that whatever ingestion process you have is knowledgeable about that particular T-SQL statement. If it is, it can be located anywhere. It's just another statement in your SQL query.
Excellent. Thank you.
Yeah.
Hello. Hi, Matt.
Hello?
Question about a queue for communicating with SQL Azure. You said that I just want to know the context of 500 per second limit.
Yeah. Yeah.
And an actual context of what that queue represents, whether or not it's a connection string user, and whether the connection string across, say, 10 instances is all connected to the same database.
Okay.
Is that defined as a single queue? So I'm just wondering where my bottleneck might be.
Yes. Okay. So maybe I described it in an unclear way. The 500 requests per second has nothing to do with SQL Azure. It only has to do for Windows Azure Storage queues. And so if you have a queue in Windows Azure Storage, you can deal with 500 transactions per second on that queue. One thing that people often do if they're getting near the maximum load on the queue is that they will create messages that have a payload that's larger than just the one message payload. They'll take a bunch of different discrete messages, they'll wrap them together in a single message, and they'll enqueue it. And it can be a relatively large message that goes onto the queue. And then that way, when you dequeue the message, you end up having a set of different requests all within the one blob that you dequeued, and you have to, or stream that you dequeued, and you have to then treat them separately. But that's one approach for achieving higher scale than 500 messages per second on a queue. The other thing that it applies, and so that's the scope of that is a single named queue. When you create a queue, you give it a name, and that's what that threshold applies to. The other way around it, of course, is to create multiple queues, perhaps distinguished by priority or distinguished by destination or not distinguished by anything, and your roles can just pull a whole bunch of different ones, and then you can, obtain arbitrarily high numbers of messages per second by using those multiple queues. As far as a SQL Azure database goes, the size and throughput limitations apply to a single connection string, unless you're using SQL Azure federations, in which case they apply to a single federation. We'll probably have updates to the documentation once federation has been fully released that describes those scalability targets or single machine limits in the context of federations in more detail. Any other questions? Well, thank you all very much for your time. Thanks very much. And have a great rest of your conference, such as there is.